Hello everyone, here are some important questions on Eamcet exam. So first question is, which of the following statements are correct? First statement is CO2 has no dipole moment whereas SO2 and HO2 have dipole moments. And second statement is SnCl2 is ionic whereas SnCl4 is covalent. So let's talk about the first statement. It says CO2 has no dipole moment. First of all, we should know the structure of CO2. We all know that CO2 is a linear structure. Okay, now let's see here that due to the great difference in electronegativity between these two atoms, that is carbon and oxygen, oxygen is more electronegative than the carbon atom. Okay, that means the delta negative will be produced here and there will be delta positive charge over the carbon atom, and similarly there will be delta negative charge on the oxygen atom. Okay, due to this partial polarity there will be the dipole moment and its direction will be from positive to the negative. So here is the dipole moment in this direction, and for this there will be the dipole moment in the opposite direction. Now because these two dipole moments are of equal magnitude and they are in the opposite direction, so they will cancel out. So the dipole moment for the whole molecule will be 0. So net dipole moment for this molecule will be 0. And on the other hand, for SO2 and H2O, SO2 and H2O do not have this type of linear structure. They have the bent structure like this. SO2 has linear structure like this, and for water it also has the bent structure like this, like this, oxygen and H and H. Now in this, the oxygen and sulfur, the dipole moments will combine and it will give the net resultant dipole moment, and also in water it will be like this. It will be the net dipole moment. That means net dipole moment, that is resultant dipole moment, is not equals to 0, and in this case also the dipole moment is not equals to 0. The net dipole moment will not equal to 0. So the first statement is very correct, which says CO2 has no dipole moment and whereas SO2 and H2O has dipole moment. So the first statement is very true. And moving on to the second statement, it says SnCl2 is ionic and whereas SnCl4 is covalent. So on the second statement, let us suppose SnCl2 and we have wrote the SnCl4 over here. Now among these two, the oxidation state of tin, that is Sn over here, is +2, and over here the oxidation state of Sn is +4. Now due to its covalency, increased covalency, there will be the increased covalent structure. Okay, due to this +4 high covalency, there will be increased covalent structure, whereas SnCl2 will have the ionic structure. So the second statement is also correct. So the answer for this question is both A and B are correct. So this is the right answer. Now moving on to the next question, what is the correct order of first ionization energy of lithium, sodium, potassium and cesium respectively? And we have these given options. Now we know that the trends about the ionization energy. Firstly, we should know where these elements fall. Now lithium, sodium, potassium, rubidium, cesium, these elements comes under the first group of the periodic table. So we know that in the periodic trends, for the ionization energy particularly, if we go from top to bottom, the ionization energy or ionization enthalpy decreases. It's the trend. And if we go from left to right in a periodic table, the ionization energy often increases. So these elements we have asked about comes under first group of the periodic table. So the ionization energy will be least for the cesium and higher for the lithium. So among these options, lithium would have the higher amount of the ionization enthalpy, that is lithium will have the higher amount and cesium will have the lowest amount of the ionization energy. So for the lithium, we'll select the higher number, that is 520. 520 will be for the lithium and least for the cesium. Cesium will have the least number. Here 374 is the least, and that will be for the cesium. Now we can write it as this is for the cesium, this is for the lithium, highest and lowest we have figured out. And for the sodium, it will be the second largest number, and over among these it is the second largest number, that is it will belong to the sodium, and eventually 419 will be for the potassium. We have asked about the lithium, sodium, potassium and for the cesium. So correct option is second option. Now there is another question, which of the following statements are correct about Bf4 negative and AlF63 negative? First statement says boron aluminium differ in oxidation states. Second is boron aluminium differs in covalency. Third is boron obeys octet rule, and D is boron and aluminium are in diagonal relation. So we have drawn these structure for these molecules, and for BF4 negative its structure is this, and similarly for AlF6 its structure is like this. So focusing on the first statement which says boron aluminium differ in their oxidation states. Now let's find out the oxidation state of boron and aluminium. Okay, let us suppose the oxidation number for the boron is X. Okay, X. In BF4 negative we are talking about. So for the fluorine, the oxidation state we know that is -1, and there are 4 fluorine, so 4 is multiplied here, and it will equal to the net charge on the molecule, and the net charge on the molecule is -1. So the X value will comes out to be +3. And on the other hand, for the AlF6 negative, the oxidation state, we have to find the oxidation state of aluminium. So let us suppose the oxidation state is X over here, plus there are 6 fluorine atoms, and each fluorine atom will have the oxidation number -1, and it will equal to the net charge which is equal to the -3. So we will calculate it, and X will comes out to be +3. So we can see that oxidation number for both of the elements in each of the molecule are same. So first statement which says boron aluminium differ in their oxidation state is not correct. It's false. Again, second statement says boron aluminium differs in covalency. What is covalency? Covalency is the combining capacity. That means how many bonds it can form. Okay. So over here, what is the boron's covalency? How many bonds it is forming? Over here it is forming 1, 2, 3 and 4 bonds. So for the boron, its covalency is 4 over here, and for the aluminium, its covalency, that is bonding capacity, is 6 over here, because it is forming 6 bonds. And for the, that means it is correct. The second statement is correct because the covalencies are different, so the B is correct. And for the C, B obeys octet rule. Boron obeys octet rule. So in this, let us count 1, 2, 3, 4, 5, 6, 7, 8. Yes, it obeys the octet rule, so C is also correct. Okay, so last is boron and aluminium are in diagonal relation. So for D, we know that for the boron group, boron, aluminium, gallium, indium, thallium, it is the 13th group of the periodic table. Aluminium comes just below to the boron, so it is not the diagonal relationship, but it is the element of the same group. So the D option is incorrect. So the right options are only B and C. Okay, so the next question is, if the solubility of NiOH whole twice is given this, what is the solubility in mole per liter for this? We have to find the solubility, and we have given the solubility product. So for these type of question, we should know the dissociation, how this molecule will dissociate. Now we know that NiOH whole twice will dissociate like this. It will dissociate in nickel 2 positive ion, plus there will be OH negative, and there will be 2 OH negative, because we have to fulfill the valency over here. So let us suppose we have to talk about the solubility. So let us say it has the solubility of S. So according to the stoichiometry, which is 1 over here, its solubility will be 1S, and its solubility, OH negative solubility, will be 2S. Okay, now we have to write the Ksp relationship. What is Ksp? It is the solubility product constant. Okay, solubility product, and it is also given in the question. Now solubility product is the, how we will write the solubility product? It will be the concentration Ni, 2 positives concentration, raised to the power its stoichiometric ratio, which is 1. So we will write 1 over here, into the OH negatives concentration and raised to the power its stoichiometry, which is 2 over here. So now we will put the values. Ksp's value is 4.0 into 10 raised to the power minus 15 given in the question, and which is equals to Ni. What is the value of Ni2 positive? Its concentration solubility, that means is S. So we will write S and 1. Okay, into what is the concentration of OH negative? It is 2S and raised to the power 2. So upon calculating 4.0 into 10 raised to the power minus 15 equals to 2 to the 4s cube. S will be equals to 4 into 10 raised to the power minus 15 divided by, it will go down here, it will be 4, and raised to the power, this 3 goes to the other side, so it will be the reciprocal over here. So we will get the value of solubility, which is equals to 10 raised to the power minus 5. 5, sorry, 10 raised to the power minus 5, because 4 got cancelled and 3 5s are 15. So D is the correct option for this. Now we have to find, we have the another question. We have to find the Iupac name. We have to find the Iupac name of Isoprene. Now you should know the chemical formula of Isoprene, that you should very much surely know. Its chemical formula is CH2 double bond C bond CH double bond CH2, and there is a methyl group over here. Okay, and this is the chemical formula of Isoprene. Now we have to find the Iupac name for this Isoprene. So we should count these carbon atoms in such a way so that these substituents and these double bonds will get the lowest number. So if we count from here, suppose we count from this end, that is 1, 2, 3 and 4. So this methyl group will get the third priority. If we count from this end, that is, I am counting 1, 2, 3 and 4. So you can see that at second position there will be the methyl group, which is far more better. So we will count in this way. So for that we should know certain things, that is parent ring. Parent ring. What is parent ring numbers? Parent ring is this. It is of 4 carbon atoms, and for the 4 carbon atoms there will be buta. There will be buta associated with it. And for the primary, there will be the primary suffix. There will be the primary suffix, and it denotes the saturation or unsaturation in a molecule. That means double bond or single bond. That means there are 2 double bonds. That means there will be ene used. That means 1,3-di-ene will be used, because at 1 and 3 position there are 2 double bonds, and there will be the prefix also. Prefix will be 2-methyl, because at second position there will be 2-methyl. Okay, so we will write the full name, which is see, 2-methyl. We will write accordingly. 2-methyl, it is the Iupac name, 2-methyl 1,3-butadiene, 1,3-butadiene, or you can simply write 2-methyl buta 1,3-diene. Both the names are correct. So we have just ended with the Iupac name of the Isoprene. Thank you so much. Do like and subscribe.